Hello, everyone. I'm Jordi Baylina, technical lead at Polygon zkEVM. And last year in Paris, here in this conference, I was presenting a very challenging project, was the zkEVM. Mainly was building a zkEVM opcode compatible. That means that a zkEVM rollup where you can send any transaction the same way that our construction today, normal transaction, you send to a rollup and everything works. The biggest part of this challenge, well, we presented was the biggest challenge was to build the prover, the zk prover, so a system that you can prove that the transactions are valid. And the biggest challenge was the time to build this proof. You know, this is very zk. The EVM was not prepared to build to be a zk proof. So the question was how expensive this would be. We came up to a system, to a set of solutions that this would make it together, but this question was still open. After a year of hard work, and after, just after Paris, Polygon Hermez, at that point, we merged Polygon. Polygon also did a huge investment in other zk teams. Here, Polygon Maiden and Polygon Zero also were put on board. We start work together. We have been doing a lot of improvements. And actually, and this is the big announcement today, is that we can say that the prover is done. We have done today, and actually at this point, all the source code of the prover should be public. It should be released in GitHub. It's still a lot of work to mainnet. We will talk it a little bit later. We still, of course, the code is plenty of bugs probably today. We need to check, we need to test, we need to check, and there is still an important roadmap to mainnet, but the solution is there. And this is the big announcement that we wanted to do there. This is important because, for many reasons. First, because all this knowledge now is public, is shared, is present for the community. And this is, I think this is one of the biggest contributions that the Polygon team has made. It's not going to be the first one, for sure, but it's probably the most important one that he made in the last times. So before going to the repo, just want to give a big overview of what are the big picture, the big map of the zkEVM project. The zkEVM project starts with, I don't know if this was some, well, it starts with some smart contracts, the rollup smart contracts, and also the bridge smart contract. There is a node, it's a full, something like Ethereum node, but it's a different node in this case. It's a node that, collects transactions, build the batches of the L2. It talks to the prover just to build the proofs, but at the end, it has the JSON RPC interface, and it's exactly the same interface that Ethereum has. If you want to build an Ethereum compatible, not code compatible, means that developers should use this system transparently, the same way that they're using Ethereum. They should not see any difference at all. What are the repos? There is a bunch of repos. I'm going some deep later in some of the most important. Here is the list of one. The prover and the prover.js. We built like two provers. One is in JavaScript, which is more for prototyping and for creating test vectors and for testing and doing the things fast. But there is the prover itself, which is written in C++. It's a production-ready. It's the production-ready prover. So this is the ones that are more generic. Okay. We have the ROM, which is actually the source code of the program that executes the EVM. More on that later. We have the node itself, so the full node where you can collect these transactions and publish the RPC and so on. We have the smart contracts, we have the bridge services, and the last one, it's also important, we have a documentation. We have it's a basic documentation. It's still, of course, documentation is our constant work in progress, but at least you have, there you have an explanation of how everything works. Maybe it's basic, margin to improve, but everything is there. Then there is some secondary repos. Here we have a common.js, which is a placeholder for common functions and libraries that we use in many places. We have a zkEVM. This is the compiler of the assembly that's building on top of the processor. We have a test vectors. Here is a test suite where we are running all the tests for the EVM. And then we have a special repo for the storage. All the storage, it has the same processor. It's a specific state machine that has his own repo. And there is two things that are not directly related to the zkEVM. These are toolings. We have PILCom, which is the compiler for PIL. And then we have PIL-Stark. These repos, we'll talk about it a little bit later, but are really where you are building the Stark and where you are building the prover. And this can be used not only for the zkEVM, this can be used for building any zero-knowledge application. And they are available and ready today. Okay? So going a little bit deeper, if we dip a little bit to the prover, how the prover works, here is the main specification of the prover. What we want to do. We have a set of transactions, Ethereum transactions. We have a state root, so the current state. And we want to compute the new state. And this new state with these transactions is deterministic. So we want to prove that this new state corresponds to this old state applying these transactions. So the zkEVM internally, the way it's built, is mainly we built a kind of a processor. So we have a kind of a generic processor. It's not an electronic processor. We can say it's an algebraic processor, but at the end it's a state machine. So you have a set of registers. You have operations like multiplication, adding, moving, storing, setting to memories, and so on. And then we have a program that's executing deterministically on this processor. And it's actually this program the one that where we are processing the transactions. These instructions, this is written in assembly. We have also, for example, conditional jumps, moves. If people don't know something about assembly, they know that. But this is this processor. The important part of this processor is that it's zero knowledge. It works very well in the zero knowledge environment. Okay, so this processor, okay, executes instructions, but it has like different pieces surrounding the processor that in order for this to work. In one side we have the RAM. RAM is like normal RAM. You can do in the instructions in assembly. You can read to memory, write to memory, and you can work normally as any other normal RAM. This RAM also has, for example, we have some specific things for the EVM itself. For example, it has some paging. This allows us, for example, to do call context. So when you are when you are calling one smart contract to another smart contract, then the context of the RAM changes. So we have different pages for different RAMs and so on. So we have a paging system on that side. And we also solve for this 32 bytes alignment. You know, if people don't know Ethereum, it's a 256 bits words, but the memory is byte aligned, and sometimes you can do in between readings and in between writings. And here is a specific substate machine just to solve this specific question. We have the ROM. The ROM is actually the program that is executing. It's a program, this is part of the proof. This is the program that takes the transactions, executes the transactions, and build this new state deterministically. Okay? And we have the storage. Storage for itself is a full system. Storage is like another processor that's processing the state Merkle tree. This morning, Jesus explained it very good, the the architecture and the data and how this storage state machine. But from the proving perspective, at the end it's a processor with a specific, similar to the main one, but with a specific, with his own ROM and with some specific instructions like hashing or claiming the key and so on. So that helps to build the proving for the storage. We have other pieces. For example, we have binary and arithmetic. Binary, here we have all the instructions for AND, OR, XORs, even ANDs and subs, less than, more than. This is done byte to byte with a block up on that side. So on that, so that's done in this state machine. Then we have the arithmetic state machine. This is probably one of the biggest innovations that we can present and that you can check. Here we allow us to do 256-bit operations inside the prover in a very efficient way. But not only that, in this arithmetic state machine, we also added some specific arithmetic functions for the elliptic core that we need for the CDSA. So if you want to process an Ethereum transaction, you need to validate the signature, for example, as that's the first step. So we need to implement the CDSA. So the CDSA part is done in the main, as the main program, but some specific elliptic core operations are done in the arithmetic state machine with the prime field and in a very optimal way. And then we have all the hashing. Here we have two hashes. One is the Poseidon, which is the optimal one, the one that we use in the storage and we use to hash the programs. But then we have Ketchak, because if we want to implement a zkEVM, so EVM compatible opcode, we need Ketchak. Ketchak is not as efficient as Poseidon, but we actually did a good improvement, an important improvement. We are building Ketchak, the inner function, in parallel. People interested can check, but it's an interesting way of building binary circuits in parallel, and it's also an important innovation there. Okay? But as I explained there, the core part of this prover is the zkROM. Here is the program where we actually are implementing Ethereum. Okay? And now I want to show you some snippets of the code for you to see a little bit how it looks like. So for that, I'm going to show you the code. This is available, so you can check it. Let's see. Here is the assembly. Here we're just implementing the opcodes of Ethereum. Here is the pushes. You have here you have all the opcodes here, but you have the swaps. But even if you go to the end, there's a lot of opcodes. If you go to the end, probably the interesting ones. Here is a return and create. We have the returns. We have delegate call. We have calls, static calls. So we have all the opcodes reverts. So all the opcodes are implemented in this assembly. This assembly, as you see, is very specific. Here is instruction. Here is the movement of the registers. So it's very specific for this, but this allows us to fine-tune and to implement Ethereum. This is one example. There are other examples. For example, this is, for example, the part where we are parsing the RLP transactions in order to get all the parameters of the transaction and hashing them together, so that check that the hash is okay. So it's as you see, there is a lot of work, and here where we can fine tune and we can get a high level of compatibility between Ethereum EVM and the zkEVM that we are building. Okay, going back to the presentation. Let's see here. The other important piece. These are what we call the state machines until now. It's mainly these at the end are these polynomials plus this code. But then there is the prover itself. We need, once we have these polynomials and these polynomial equivalences, then we need to build in this case is the Stark, the first Stark. So with this we have the pill Stark. The pill Stark, this is generic. You can build your own pill and you can build your own system with that. And in Pill Stark, what's doing? So once you define a pill, once you define this polynomial identity language that defines the processor, it defines this like kind of a hardware, that's it. You don't have to do anything else. If you just build the polynomials, you build the polynomials, you want the arrays of values that fulfills these polynomials, and then you just run pill and you get automatically a prover, you get automatically a verifier, so a prover is a Stark generator, it's a verifier, and you also get, this system will also generate a circuit that will automatically verify the Stark for you, just without writing a single line of code. And not only that, at this point, with this software, if you have a circum circuit, you can also have a Stark. You can have a prover and a verifier from the circuit. So the pill allows you to do not only normal relationships, it allows you to do block-up identities, permutation identities, but they also allows you to do copy constraints or connection identities. So the system takes a circuit, it converts to these connections, so it connects these connections and gates, Plonk-like style, and then you can have a Stark. And if you have this, then we have the recursion, we have Stark recursions, because we generate the verifier will generate the Stark, so we have this recursion. And this is the basic thing, and this is the very powerful, because with this we can build this proving system that consists of a set of proofs. We start with the basic proofs that are actually the zkEVM proofs, but then we can aggregate this proof to a single proof, and we can do a system of proof where we are reducing the number of queries, or we are adjusting the Stark the way we want, and in the last moment, just the last Stark, instead of verifying it with a Stark, we verify it as a snark. At the end, it's a circuit. We compile it just for being a snark, Plonk or growth 16, and then we can validate that on-chain. At this point, we are working, the current work is very much working what's the best, what's the right, and what's the best structure of these Starks. It's one layer, 2 layers, 3 layers, how we aggregate those, and this is very much some of the work that we are working at this point. And all that, benchmarks. What's a prover? Okay, this is still a work in progress. Currently, our reference machine is just a 64-core machine. It's something in AWS, in spot instances, cost around $2.5 per hour. And processing proof that more or less processes 500K gas of Ethereum, it takes around 5 minutes. That means that if we just do some division, more or less the cost per transaction is a sub-cent cost of transaction. But the good news is that, well, this I think is good and good enough results, but we are still working in the improvement. I think there is plenty of margin to improve that parts. Here we have, of course, coding optimizations, something that you can code better. You can have some mathematical improvisations. We can, of course, improve the state machines. Actually, we already know some of the improvements we can do in the state machines so that we can use less polynomials, so we can do the things in a better way, and these are some fine-tuning and some improvements. And there is also a full topic which is GPU and FPGA, where you can have some acceleration there. Just expect some news in the coming weeks on that subject. The other part is testing. Building a zkEVM is challenging and has a lot of difficulties, but there is one thing that's very advantageous is about the testing. Because if zkEVM compatible means being compatible with Ethereum, we can take all the testing suite of Ethereum itself. And this is what we have started doing. At this point, we have started to do this testing. We started, I think it was 1 week ago or 2 weeks ago. We are already 30% of the tests they pass. At this point, this number is not important. The important part is that we are doing this. We're taking this procedure to test our system. We expect to reach, if not 100%, just very close to 100%. Maybe some of the tests will have to adapt or adjust, but this is the idea and the goal. And and finally, I want to talk about a little bit about the roadmap. And well, yeah, as I said, currently we have the system implemented. We are at this point testing a lot, fixing bugs. If you see, check the code. No, there are things that don't work. That there are bugs we are fixing. I hope that in a few weeks, most of the main bugs and stabilize that could be done. We will start opening that first in internal testnet. Later on, when we feel more comfortable in a public testnet, should be in a matter of weeks, just when this is more or less stable. And then we will start one of the most challenging phases, which is auditing all this and securing all this. And this is what will mark the launch of the mainnet. Securing this is a huge challenge. As you have seen here a little bit of a snippet, but if you check the code, you will see that there is a ton of code, a ton of new things, new ideas. Each state machine is a world itself. It has a topic, so it's a lot of things that needs to be checked, that needs to be audited, that needs to be secured, that needs to be reviewed for many of you. And here is a call that I'm doing to the community. We really need help on that. Please, people that's interested in this technology and in this system, go to the code, contact us if necessary. I'm going to try to talk to as many conferences, to as many workshops, to as many places, to explain this system in as much detail as we can. Opening the source today, it's the first step for securing this system. And if you want to launch this in mainnet, we need to work together to review, check, and be comfortable, be confident to launch. We are not going to launch anything until we don't feel confident that this is safe enough. And that's it. That's my presentation. Thank you very much. Exciting times are coming, and just maybe before just taking some questions, I just want to thank you to so many people, starting from the team that starting from maybe from the Prover team, but then from the Hermez team, all the Polygon family, all my partners, of course the Polygon founders just for believing in us and betting in us, and of course also my family and everybody that's around and all the community, because this is a huge effort, and I really want to thank you to everybody that has made this possible, and it's continue possible. A lot of exciting times in the upcoming weeks, so please, if somebody have any question, I'm glad to answer. I don't know how yeah, I think we have 45 seconds, so. I cannot believe nobody has a question.
Hey. Yeah, thank you very much for the presentation. Just one question. If you talk about launching mainnet, what does that mean? Will this be a new network that is kind of then proven on Ethereum, or a new network on Polygon, or would that mean kind of transforming Polygon to something zkEVM based? So what does launching mainnet mean?
That means mainly a mainnet built on top of Ethereum.
Okay.
We are just going that question. Here, Polygon is very committed to Ethereum. We are using the Ethereum technology. We want to build this because it's Ethereum compatible. We are part of the Ethereum family, and if we are here, it's because we believe in Ethereum. So the goal is to scale Ethereum with this. More questions? So let's keep it here if you want, because it's a little late. So thank you very much again, and any questions, just ask.